OK, so now we get to what can software do for my cache? And what can software do for my memory system? Well, surprisingly a lot. And compiler people actually do spend a fair amount of time thinking about this. So one of the things you'll actually see is you'll see the compiler many times pad out data structures. So if you go disassemble a piece of C code that you have, you'll actually see the compiler many times will insert extra bytes, which wastes memory, but it's there to improve performance. And how this improves performance is it'll make the access patterns, for instance, either not conflictive in our cache or conflict in our cache in a strange way, which is beneficial, or will somehow exploit either temporal or spatial locality. So you can do lots of tricks here to either improve spatial or temporal locality. One of the things I did want to talk about is sort of a hybrid software-hardware solution here that you can actually add instructions to your processor to give hints, to allow the compiler to give hints to the architecture whether to pull something into the cache or not pull something into the cache. So many times the compiler will actually know, or the programmer will know, I need to use this data exactly once. Now, if you know you only need to use that piece of data once, should you pull it into your cache? No. You're never going to reuse it. You're never going to get a cache hit. You're just going to take the cache miss, and then at some point later in the future, you're just going to evict it, and it's going to hurt your miss rate. So instead, there's been an introduction, actually, of sometimes people call this non-temporal hints or no allocate bits. So one way this actually works out sometimes is certain pages in our memory system are marked as being non-temporal, and it won't be cacheable. You can do this on x86. Actually, there's non-cacheable bits in the page tables, for instance. A finer-grained way of doing this is actually having special load instructions or special store instructions, which say, do not ever bring this into my cache, or do not pollute my cache with this data, because I never intend to go read this again. And lots of architectures have started to include this now as an optimization. Another fun thing you can do is if the compiler or the software system or the programmer knows that you're never going to use the data again, why let it sit there and rot in your cache? Get it out. Get it out as quickly as possible. Now, there's a couple different ways to do this. So one of the instructions that you can add to the architecture and have a software-hardware approach to this is you'll actually add something that I think on x86 is actually called flush and invalidate. So the idea is that you may still have dirty data in that location, and you want to flush it out to main memory, or flush it out of my cache, and invalidate the data in the cache. And by giving the compiler or the programmer fine-grained control of this, you can effectively kill data that is in the cache and make it clean, or make it clean and not valid in the cache, that line. So when you go to bring in new data, you don't have to evict something. So you're effectively, it's kind of the inverse of prefetch. In software prefetch, you bring something in early. Here, we push something out early. And that can be a pretty big benefit. One of the other things is that I don't quite have this on. I don't have this on the slide here, but there's a corollary to this. Lots of times architectures will have an instruction called. Basically, it's just an inval instruction. It'll invalidate the data. And the semantics of this are a little bit, you have to be a little careful with, because this inval does not flush the backing data out to main memory. You're changing architectural state with this instruction. So if there was dirty data, you're effectively deleting that dirty data. Sometimes people will actually use an instruction similar to that instead of a flush and invalidate if you know that you just have scratch pad memory, or you don't need the backing data. And that's a way to, you don't have to waste the write back bandwidth to your L2 or your L3 or your main memory. You can just say, this data is now dead. I never want to use this again. So that's typically an inval instruction. And inval instructions will lots of times take a cache line number instead of an address. Sometimes they'll take an address, and it'll validate the entire cache line. Unfortunately, you need to take the entire cache line or cache block and throw it out. And finally, the inverse instruction of that instruction, which a couple architectures have. I know Alpha has. I think x86 has later added it. I don't know what's called in x86. On Alpha, it's called, it's like something called like write 064, I think is what it's called. Basically, what you can do is if you have some data and you want to write some data to your cache, but you don't want to have to go pull in the backing data, because that will just effectively add bandwidth out to your main memory system or out to your higher levels of cache. Instead, what you can do is there's a special instruction which will just fill a whole entire cache line of zeros out of nowhere. And what's nice about this is now that you've filled an entire cache line of zeros, you can go do writes to those zeros and fill it in with useful data and never have to have gone and fetched the background data from main memory. So it saves bandwidth. So these are all different hardware, software techniques together that the compiler can use to optimize performance. But yeah, I do want to just finally one last thing about this improving spatial locality and temporal locality. If you ever go disassemble a C program, you'll definitely see structures. If you run a C program with feedback-driven compilation, you'll see that a lot of times they'll actually reorganize the data structure. And languages, so for instance, if you go look at the careful description of what C says about this, some languages allow you to insert padding or reorganize some of the fields in a data structure. And by doing that, you can get more performance by effectively reorganizing the data so you put all of the things that you access in a row right next to each other. And that'll get you, for instance, spatial locality. OK, so now we get to go to some of the fun software optimization strategies up here. So let's go to the first one here. I'm going to give you guys a second to look at this code. Look at the top example first, or the top piece of code first. We have a loop around a loop. For j is less than n, for I is less than m. OK. So it's a doubly indexed array, x here. We're effectively striding through this array somehow. And we're multiplying every element in the array by 2. Seems basic enough. So one of the questions that comes along here is, in C, the default layout of X, it's a doubly indexed array. And we're walking by the higher index is the inner loop here. So if we look what's happening here, this is a 2D array. X. And I goes that way, and j goes that way. Now we're walking through this array by I. So we're going to walk down, in that pattern. By default, in C, this array gets laid out such that the second index gets laid out contiguously. And the higher order index gets laid out non-contiguously. So this would be address, let's say, 0. This would be address 1. This would be address 2. This would be address 3, 4, 5, assuming these are all bytes. And then we come back over here, 6, 7, 8, 9, 10, 11. Unfortunately, with the way that the top loop is written, we're effectively hitting, we're fighting spatial locality of the cache lines. Huh, that's not good. Well, lo and behold, if we do the exact same operation, and our compiler can easily detect this, and we just flip the order that we stride through the array, we'll take going this way through the array, and instead, we'll go that way through the array and get spatial locality perfectly. So by doing a simple loop interchange, life gets a lot better. Actually, before I move on here, I do want to say this brings up a good example of packing of data. I have something here which has 6 bytes in a row. 0, 1, 2, 3, 4, 5. Now, one optimization that compilers will many times do is they'll actually pad out this structure, let's say out to 8 bytes, because it makes the math a lot easier to go stride through the array indices. So that's an example of one of the things that I showed before. It'll also sometimes even have better cache performance, because you'll pull in an entire line at a time versus straddling different cache lines if you have a non-naturally aligned structure like we had before. That may not happen in this, it may not hurt in this example if you're striding through the entire array. But other examples, it could definitely be harmful if you are trying to operate a lot within one row, for instance. OK, before we move off of loop interchange, does that, actually, what type of locality does this improve? Spatial, yay, we drilled that one in down pretty well. OK, so let's look at our next piece of code here. For I less than n, we multiply b of I times c of I and deposit it into a of I. And then the next loop, we do something very similar. We take c of I multiplied by a of I and deposit it into d of I. Well, you're going to say, how does this happen? This seems like a brain-dead way to write this piece of code. Yes and no. Maybe you do something in between here, between these two for loops. And it may not be readily apparent to everybody that you can actually do anything about this. Like, because you have some piece of code here which goes and reads, I don't know, all of A, for instance. Well, the compiler can recognize this and actually say, well, we just wrote this entire array. And now we go back and just read this entire array. And we read C before also. That's not very, very good. Because we're effectively, let's say these caches are, these arrays are large. We're going to read in C an element of C, read an element of B, deposit an A, and we're basically going to stride through the cache. And all these 3 arrays are going to kick each other out. But by the time we get back to here, A of 0 is definitely not going to be in our cache. Maybe A of the last element will be in our cache, or A of n will be in our cache, or A of n minus 1 will be in our cache. But A of 0 is not going to be in our cache. So our compiler can think real hard about this and do what's called loop fusion and pull these statements apart, such that you take b of I times c of I, put it here, and then use that. You're probably actually going to do that in a temporary variable. You're probably not going to do that through main memory if you have a of I and a of I in statements right next to each other. But you still have to write a of I, we'll say, for program correctness. And you take A of I and C of I, multiply them times each other, and put them into D here. What's nice about this is you're actually going to bring in a cache line of B of I, bring in a cache line of C of I, do the multiplication. You're going to bring in, well, you already have A of I because that's your destination, and you just have that in a variable. And then you can write it over into D of I and stride through all those cache lines together, and effectively you are not having to go refetch A of 0 multiple times. Instead, you've fetched it once. And what's also nice, you don't have to go refetch, let's say, C of I twice, or C of 0 twice. It's already there in your cache. OK, so question comes up here, what type of locality does this improve? Temporal, yes, because before we were bringing something into the cache, kicking it out of the cache, bringing it back into the cache. Both these actually exhibit decent spatial locality actually already, and we didn't really change the spatial locality of what's going on here. They're both striding through arrays spatially, but temporally we don't have to kick we don't have to kick A and C out of the cache effectively twice, so we're bringing it into the cache twice. So we're able to exploit a bunch of spatial locality here. Or sorry, able to exploit a lot of temporal locality here. OK, so now we get to something a little bit more sophisticated. Matrix multiply. Common thing for computers to do. You want to take, at least in dense matrix codes or linear algebra sorts of codes, you take matrix A, you want to multiply it by matrix B. So this is like traditional MATLAB kind of code. You have some MATLAB, you have a big array, you want to multiply it by another array. And let's take 2D matrices. This applies to higher dimensional matrices also. But it's easy to draw two-dimensional things on a two-dimensional screen. It's hard to draw four-dimensional things on a two-dimensional screen. So we'll start with that. Here's our naive implementation. We got 3 for loops going on here. And what we're doing is we're doing the traditional way that you learn how to do matrix multiplication. You take a row, multiply by a column, and that's that spot. You take this row, multiply by that column, that's that result. This row by that column, that's that spot. This row by that column, there. And you just work through it. And you're basically, let's step through actually what the multiplication actually is. You take this value, multiply by that value, take this value, multiply by that value, and you continue going down and summing each of the multiplication results. And that's how we ultimately end up with this point here, or this value here. So this is the input, input, output. OK, let's think about what this does to our cache. OK, let's say our cache line, these elements here are bigger. They're not just 1 byte or 1 word. They're a couple words, or they're maybe like a long or something like that. They're a big data structure, or a big value. And let's say only 3 values fit in a cache block or a cache line. So when we go to this multiply, we basically have to bring in 2 lines for this 1 row. And then over here, if cache lines are arranged this way, as we go down this column, we're bringing in different cache lines and only using 1 value out of that cache line. Well, that's not super great. Make matters worse, let's go look at the output array. The output array looks relatively similar to the input array. We're writing here, writing here, writing here, writing here, writing here, writing there. So we're just kind of streaming through memory here. I don't know if we can do better. That's a good question. At least we're going, at least the way how this code is written, we're going from left to right. So we're actually taking advantage of spatial locality. We could be doing worse. But just to recap here, this is pretty poor cache accesses. We're bringing many cache lines They're all going to fight each other, especially for large arrays. And over here, we're pulling in line after line, even though one of the interesting things is after we do this multiplication times that, we're going to do this multiplication by the next one, which sounds good. You know, this times this times this. We should be getting temporal locality here. But the downside is for very large sized matrices, as I said, this can be multiple blocks or multiple lines long. What's going to end up happening here is this may conflict with something else farther down if it's a very large cache in its own array. Or you're just increasing the occupancy into the cache. So we're going to talk about blocking, which will actually make it so that we can actually only read one block at a time and do the multiplication in multiple steps. OK, so the code gets a little bit more complicated when we go to blocking our cache, or blocking our memory multiply. Sometimes people call this tiling instead of blocking. I think tiling is traditionally sort of meant as a matrix multiplication specific term to a more general thing, which we'll call blocking. Code gets a little more complicated. But what we're going to do here is we're going to start off by here and multiply these three elements by these top three elements and deposit it into the result. Now, you might say to yourself, that's not the result that needs to go there. It's not. It's only half of the result that needs to go there, in fact. So you need to do something. You need to finish this multiplied by that and add what was here before with that new value. But the nice thing is addition is communicative, so we can reorder these steps. And in fact, what we're going to do is we're going to block or tile and have this block rotated, multiplied by that block, and deposit the results here. And then, in our next step here, if you see, we're actually going to sum into the same destination. So the first step is we're going to take this, multiply by that. And what we're going to see here is we're going to have 1, 2, 3 cache lines. And over here, we're actually going to have 1, 2, 3 cache lines. Even though we're accessing them this way, we actually design this algorithm such that we reuse that other portion of the data we pull in here. And then we're going to do that and sum the partial parts of the multiplies into these 9 locations. And then we're going to do the second half of that. We're going to take this, multiply that, and accumulate them into there. As you can see, this actually is going to have some better locality, which we'll talk about in a second. And we have to bring in fewer cache lines at the same time and still get good performance. OK, so let's look at the, if you want to compute this part over here, because we talked about in this example here, computing this entire result array. So how do we compute that part over there? Well, it's the same idea. You're going to take this, multiply by that, deposit it there, and then take this, rotate, multiply by that, and accumulate it into there. So couple things just to recap here. Couple happy things about this. We're really able to shrink the working set in our cache. So our cache capacity is lower for what's really going on here. Or rather, our effective cache load is lower. The number of cache lines we need to keep in our cache is quite a bit lower. We also can have better, so that's going to be temporal locality. Because we're basically going to have the data in our cache, and we're going to be working on the data in our cache. Now, we also end up with, if you look at the input array here, we're also going to have better spatial locality. Because before we were sort of streaming through all these different cache lines, and now we can work on one block at a time. And especially in our result matrix, because this and this reuse these entries in our result matrix twice. So we can get some benefit out of that. But so the answer is you get both temporal and spatial locality improvements here. But it's a fun software optimization you can do that will improve your performance. OK, so let's go look at compiler memory optimizations and what we can get out of this. Well, we can get some different things out of this. If you do the cool tricks where you have non-temporal hints, to some extent you can use that to increase your bandwidth because you're utilizing less bandwidth. Hit time, I don't think we're really going to allow software to change the hit time. That's a hardware constraint, so we're not going to have anything to do about that. Miss penalty, we might be able to help out with. So how does the compiler help out with miss penalty? Well, it can schedule the data so that it's in closer, for instance, the blocking algorithm will actually use a smaller cache footprint. So it'll fit into a smaller cache. So we won't have to go out to the L2. So a good example of this is, let's say you have a matrix multiply. In your matrix multiply, it fits in your L2. The naive approach fits in your L2 but doesn't fit in the L1.